In this video, I'm going to be deriving an important trigonometric identity that I'll be using in Laplace transforms. This has to do with combining sines and cosines into a single function that's either a sine or a cosine with a phase angle. So we're going to start. We assume we have some y of t which is equal to a times the cosine of omega t plus b times the sine of omega t. Now we're going to write this in terms of complex exponentials. So we have a times e to the j omega t plus e to the minus I omega t. I and j are both square root of minus 1. And that's going to be over 2. This is our cosine equivalent in exponentials. Plus b times e to the I omega t minus e to the minus I omega t, and this will be over 2i for the sine. Now I'm going to expand this out. So we have I'm going to pull out the a and b's on this thing, combine the e to I omega t, the positives and the negatives. So if we take e to the I omega t, then we have a over 2 from this term, and then we have a plus b over 2i. And we have plus e to the minus I omega t. We have an a over 2 from this term, and then a minus b over 2i for this term. Now I'm going to multiply through by 2 so I don't have to carry the 2 along. So I'm going to write this as 2y equals e to the I omega t times a minus ib. The I in the denominator, when we bring it up into the numerator, we get a minus. If I multiply numerator and denominator by I, the numerator has I, the denominator has I squared, which is a minus 1. And then we have e to the minus I omega t times a plus ib. The same thing happens here. When we bring the I up, we change the sign and we get a minus minus, which gives us a plus. Now, I'm going to look at these two complex numbers. A minus IB, I'm going to represent this as R e to the I minus I phi, where R squared is a squared plus b squared, and phi is the angle whose tangent is b over a. That's what this complex number represents. This is the magnitude, and then the angle is the arctangent of the imaginary part over the real part. And since it becomes a minus b over a, the arctangent would be negative, and I'm incorporating that negative right here, rather than writing it into the arctangent. Then A plus IB will be R e to the positive I phi, because these are just complex conjugates. If this is a minus phi, the conjugate will be opposite sign of plus phi. Now, I'm going to write this on out, substitute these in for A minus IB and A plus IB. So we've got 2y is equal to e to the I omega t times, for A minus IB, we have R e to the minus I phi plus e to the minus I omega t, and for A plus IB, we have R e to the I phi. Now, I can pull out the magnitude R, and I can combine exponents. We have the same base, so we can combine the exponents. So this becomes e to the I omega t minus phi for this term. And then this term, I'm just going to write this as R. Then this becomes plus e. We have a minus omega t minus phi. If we look at this, we have minus I omega t plus phi. If I write it at, or I phi, if I write it as a minus I, I've got omega t minus phi. So this becomes a minus I omega t minus phi. Now we recognize this. This is of the proper form to give us a cosine. E to the I angle plus e to the minus I of the same angle. So I bring the 2 down as I have here. I'll take the 2 from this side and divide it through. Now we see that we have the cosine. This is R times the cosine of omega t minus phi. Now, if I take this equation and multiply it by I, then we can get a new form. If I multiply this by through by I, I'll have 2iy is equal to e to the j omega t, and then I multiply through by I here, so this becomes IA minus IB times I, and minus I squared is just plus 1. So this becomes B plus I A. We're multiplying through by I, so we get IA, and then a minus I squared, which is a plus 1, so we just have B. Then we have e to minus I omega t, and again we're multiplying through by I, so we have an I squared B, so this becomes minus B plus I A. And I can rewrite this now in a form where I'm going to pull out a minus sign. So we have e to the I omega t times B plus IA minus e to the minus I omega t times I'm pulling out the minus sign, so we have a b minus IA. Now, similar to what we did here, I am going to write the quantities in the parentheses as in polar form. So we have b plus IA is equal to E or R, the magnitude E, R, E to the I, I'll call it psi, a different angle. And psi is the angle whose tangent is the imaginary part over the real part, or the arctan of A over B. That takes care of this. B minus IA is a complex conjugate, so in a similar manner, this will be R e to the minus I psi, because it's a complex conjugate. We just take the negative of the angle. And again, R is A squared plus B squared, just as it was here. So now I can rewrite this equation I'm going to go ahead and group, rewrite, put this in polar form, these two in polar form. So I have 2IY, which is equal to E to the I omega t, and B plus IA is R e to the I psi. And then we have a minus E to the minus I omega t, and B minus IA is R e to the minus I psi. Again, we can combine the exponents and pull out the R. We have R times, this is E to the I omega t plus psi minus E to the minus I omega t plus psi. We have a minus minus, we pull it out, and it's omega t plus psi. And now we can divide through by 2i. So our y now, y of t, becomes r times e to the I omega t plus psi minus e to the minus I omega t plus psi over 2i. We recognize this form as being the sine of omega t plus psi. So y of t can also be written as r times the sine of omega t plus psi, where psi is given by this, and r is a squared plus b squared, the square root of that. So we have two forms now that we have for the sine, the sum of two trig functions. A cosine omega t plus b sine omega t is equal to r cosine omega t minus phi, or r sine omega t plus psi. So I'll go ahead and write this in a summation form here. So y of t is equal to a cosine omega t plus b sine omega t, and it can be written as r times the cosine of omega t minus phi, or r times the sine of omega t plus psi, where phi is the arctangent of b over a, and psi is the arctangent of a over b. And r squared is a squared plus b squared. Now, we can see a relationship between psi and phi in the following manner. Suppose we add them. What do we get? Theta plus psi is the arctangent of b over a plus the arctangent of a over b. Suppose we take the tangent of both sides. So the tangent of phi plus psi is a double angle formula, and for tangent, that is the tangent of phi plus the tangent of psi over 1 minus the tangent of phi times the tangent of psi. Now, the tangent of phi is the tangent of the arctangent of b over a, which is b over a. And the tangent of psi is the tangent of the arctangent of a over b, which is a over b. So putting them in here, the arctangent of phi is b over a, plus the arctangent of psi, which is a over b, divided by 1 minus the tangent of phi, which is b over a, times the tangent of psi, which is a over b, and we see that the denominator goes to 0, because this becomes 1 minus 1, or this approaches infinity. Well, the tangent of an angle that is infinity means that the angle is pi over 2. The tangent of pi over 2 is undefined. It goes to infinity. So then we conclude that the tangent of psi and phi being infinity, that phi plus psi is equal to pi over 2. So that's the other relationship we have here, is that phi plus psi equals pi over 2. So if you know one, you know the other. I am now going to derive the law of cosines using complex variable techniques. Here we have the complex plane. We've got the real and imaginary axis, and within the plane I have two general points, z1 and z2. These 2 points, along with the origin, define the apexes of a triangle. Now, z1, point z1, is defined by a position vector going from the origin to z1, and it has a magnitude or modulus of r1. That's the distance between the origin and z1. z2 has a modulus of r2, and the vector going from the origin to z2 defines the position of z2 in the plane, and that distance from the origin to the point just happens to be the magnitude or modulus of z2. Now, the angle that the vector, position vector for z1 that it makes with the horizontal positive real axis is theta 1, and the angle for z2 is theta 2. And I will define the angle of this portion, this interior angle of the triangle, as R3. And as we can see from the diagram, theta 3 is theta 2 minus theta 1. Now, this angle is not the same as the angle defined by Z3, which is, we will form Z3, which equals the difference between the two position vectors, Z1 and Z2. Z2 minus Z1 is a vector pointing from Z1 to Z2. And we can see that by writing this as Z2 plus a minus Z1. So if Z1 goes from the origin to Z1, then minus Z1 is in the opposite direction, the same length, but in the opposite direction, parallel. So Z3 would be Z2 minus plus a minus Z1. So we have Z2 plus a minus Z1. We go head, tail to head, tail to head. So Z2 minus Z1 gives us this vector going from the origin there, and that is parallel to this side and in the same direction. So the third side of the triangle can be represented as Z3 equals Z2 minus Z1. And we're only concerned with this interior angle of the triangle. These other two interior angles are not in general represented in it and don't have any relationship to the angles associated with Z1 and Z2. Now, let's write down some of the relationships we know regarding complex numbers. Z defines a complex number, and in polar form it's e to the j theta. Its complex conjugate has the same magnitude but the opposite angle. So it's Re to the minus I theta. Now, a complex number times its conjugate is its magnitude squared, which is R squared. And we know that conjugation distributes through addition. So if we have Z1 plus Z2 conjugate, this is Z1 conjugate plus Z2 conjugate. And it also distributes through multiplication. So Z1 times Z2 conjugate is Z1 conjugate times Z2 conjugate. Now, we can now start manipulating these complex numbers. Let's start with Z3 equals Z2 minus Z1. So R3 squared, the magnitude of Z3 squared, is represented this way. And putting in for Z3, this is the magnitude of Z2 minus Z1 squared. But we know that the magnitude squared is just a complex number times its conjugate. So we could write this as Z2 minus Z1 times Z2 minus Z1 conjugate. Now, we can distribute the conjugation through the subtraction. So we have Z1 minus Z2 times Z2 conjugate minus Z1 conjugate. Now we'll expand this out. We have Z2 times Z2 conjugate We have a cross product, minus Z1, Z2 conjugate. The other cross product, minus Z2, Z1 conjugate. And then a minus Z1 times minus Z1 conjugate, which is a plus Z1, Z1 conjugate. Now we know the complex number times its conjugate is its magnitude squared. So we can write this as magnitude of Z2 squared plus the magnitude of Z1 squared. And we'll combine these in one set of parentheses. So we'll have minus Z1 Z2 conjugate minus Z2 Z1 conjugate. Now I'm going to rewrite this particular expression right here, Z1 Z2 conjugate. We can write it as Z1 conjugate Z2 conjugate and substitute it in. See, this, the motivation is so that this looks like this. Now, Z1 or Z2 magnitude squared plus Z1 magnitude squared, we can write it as R1 squared plus R2 squared, where the R1 and R2 are just the magnitudes. And then we have minus, I'm substituting this in for this expression. So we have Z2 times Z1 conjugate minus Z2 Z1 conjugate. That's this portion here. Z1 Z2 conjugate can be written as Z2 Z1 conjugated minus Z2 Z1 conjugate. Now let's consider this expression within the brackets. We have Z2 times Z1 conjugated plus Z2 Z1 conjugate. Now these are the same complex number, Z2 Z1 conjugate. So we're taking a complex number and adding to it its conjugate. Remember that if we take a complex number and add to it its conjugate, we get twice the real part of that complex number. So this is twice the real part of Z2 Z1 conjugate. Now let's express this in polar form. So this becomes let's look at Z2 Z1 conjugate. Writing this in polar form, we get R2 e to the j theta 2 times R1 e to the j or I theta 1. I keep mixing them up between what mathematicians and engineers call it. These still represent the square root of minus 1. So we have R1, R2, e to the j. This is Z1 conjugate, so this has to be a minus sign. Z1 would be R1 e to the I theta 1, and the conjugate is minus. And now we can combine the exponents, so this is I theta 2 minus theta 1. Now from our diagram, we see that theta 2 minus theta 1 is this interior angle, which I'm calling theta 3. So we can write this as R1, R2, e to the I theta 3. We have that theta 2 minus theta 1 equals theta 3. Not to be confused with the angle that Z3 is. The angle of Z3 and this theta 3 are not the same. This theta 3 is the interior angle of the triangle and has no relation to the angle of Z2 minus Z1, which is Z3. Just to keep that straight. Now, the real part, as we see, if we look at the real part of Z2, Z1 conjugate, that will be equal to, writing that down, the real part of Z2, Z1 conjugate is R1, R2 times the cosine of theta 3. The real part of this complex number, here's our complex number, and remember from Euler's identity that the real part, that this number can be written as R1, R2 times the cosine of theta 3 plus I times the sine of theta 3. The real part is this portion right here. This is the real part, R1 times R2 times cosine theta 3. And that's what we have here, the real part. So we can write now twice the real part of Z1, Z2, Z1 conjugate is this expression here. And this expression is twice the real part, or 2 times. This is twice R1, R2 times the cosine of theta 3. That is this portion right here. So rewriting it, we have now R3 squared equals, this portion is R3 squared, and it's R1 squared plus R2 squared, and then we have a minus twice R1, R2 times the cosine of theta 3. So recapping this, this is the law of cosines. That is, the magnitude of the third side of a triangle is equal to the sum of the squares of the other 2 sides minus twice the product of the 2 sides times the cosine of the angle between the other 2 sides. So for the law of cosines, what we have is this. So the law of cosines tells us that the magnitude of this side squared is the product of this, or the sum of the squares of the other 2 sides minus twice the product of the other 2 sides times the cosine of the angle between them. This is the law of cosines. Here I have a summary of the important trig identities and some of the important characteristics of complex numbers that's been discussed so far. Here is the Euler identity, or what's called Euler's formula, that e to the I theta is cosine theta plus I sine theta. Why this is important is that it relates the exponential form of a complex number into a trigonometric form. And we have, when theta is equal to pi over 2, cosine of theta vanishes, sine of theta is 1, and we're left with I. So I is e to the I pi over 2. This is called the imaginary unit. Now, using Euler's identity and properties of exponentials, we have e to the I theta raised to the n power is e to the I n theta. And this portion, using Euler's identity, substituting in n theta for theta, we get cosine n theta plus I sine n theta. And then e to the I theta is this portion. We can raise it to the n power. So we have a expansion that we can do using the binomial theorem. And the binomial theorem is this, where we have two monomials added together, which forms a binomial raised to the power n, and it's just a summation using combinations to determine the coefficients, and then we have a decreasing value of exponent on A and an increasing value of exponent on B. And again, we can get these coefficients by forming Pascal's triangle. I also derived the law of cosines, which is, if we have a triangle, that if we want to find an unknown side, if we know two sides and the angle between them, we can compute what the third side is. In this case, this side R3 will be R3 squared is a product summation of the sum of R1 squared plus R2 squared minus twice the product times the cosine of the included angle. Or I could go in on another side. Suppose I want to know R2, but I know R1 and R3 and the angle between them. So in a like manner, I would write R2 squared equals R1 squared plus R3 squared minus, this should be twice R1, R2. So this would be minus twice the product of R1 and R3 times the cosine of the angle between R1 and R3, which is theta 2. So the way I have things designated here is angle theta 2 is opposite side R2, angle theta 1 is opposite side R1, angle theta 3 is opposite side R3. So this is the law of cosines. Now, also have some properties of complex numbers, that if we add a complex number and its conjugate, we get twice the real part of the complex number. If we subtract the conjugate from the complex number, we get 2i times the imaginary part. And we can distribute conjugation through an addition like this. Z1 plus Z2 conjugate is Z1 conjugate plus Z2 conjugate. And the conjugation also distributes through a multiplication. So Z1 times Z2 conjugate, that quantity conjugate, is just Z1 conjugate times Z2 conjugate. And our designation for a complex number is Z equals X plus IY, where X is the real part, Y is the imaginary part. The imaginary part does not include the I. Real and imaginary parts are always real numbers. Now, the important identity that I came up with here, you don't find in too many books, is that if I want to add a sine and a cosine together, where they have differing amplitudes, the amplitude on cosine is A, the amplitude on sine is B, they both have the same argument, then the sum of a sine and a cosine can be written either as a cosine of the argument with a phase shift phi, or as a sine with the same argument with a phase shift psi. And the amplitude of this combined sinusoid is the magnitude squared is the sum of the squares of the amplitudes of the sine and the cosine. And phi, the phase shift on the cosine, will be the angle whose tangent is the ratio of the sine amplitude to the cosine amplitude, and when you're writing it as a sine, the phase shift is the arctangent of the ratio of the cosine to the sine, and then the two phase shift angles between sine and cosine is shifted by pi over 2. And here I have a graph to illustrate it. Is a cosine theta is in black. That's the black curve here. Cosine starts out a maximum when theta is 0. When theta is 0, the cosine is 1. And so we're at maximum amplitude at A when theta is 0. And then as theta increases, the cosine decreases until it reaches pi over 2. This value here will be pi over 2. And then this value here is pi. And this will be 3 halves pi. And then this value here is 2 pi. 2 pi is 1 period, as we can see for the cosine. We start out at maximum, we go through 0, we reach a negative maximum, go through 0, and then we're back where we started 2 pi radians later. That's 1 complete cycle on the cosine. Now the sine we have the same way, and that is in green. The sine curve in green, sine always starts out at 0. I'll put this as green. And the cosine, I'm sorry, that's put it in the wrong place. Gosh. The green is the sine. Yeah, ignore this. I'll just write this as like that. Shoot. Kind of messed that up. Okay. I'm sorry, the cosine is in black. All right, so the cosine curve is in black. The sine curve is in green. So sine starts out when theta is 0. It starts out at 0. At pi over 2 radians, it reaches a maximum, which in this case is B. And then it goes through 0 at pi, reaches a negative maximum, and then goes through 0 at 2 pi. Again, the sine has a period of 2 pi, but it's shifted relative to the cosine. They're out of phase, what we say out of phase, by 90 degrees. Their maximums differ by pi over 2 radians, and the same with their 0 points. They differ by pi over 2 radians. So our sine curve is in green, and our cosine curve is in black. Now we're adding the two. So point by point, what you do is you take, say, pick a point time in time here, and you just sum the two values on the two curves to come up with the new value. This plus this gives us this point on the red. So the red is the combined sine and cosine curve. And as you can see, it also has a period of 2 pi. But it's shifted a little bit. It doesn't start out at its maximum, nor does it start out at minimum at 0. It's shifted a bit. And the amount that it's shifted we call the phase shift. And that's what your theta is. If you represent it as a cosine curve, it's shifted to the right. Because see, here's our cosine curve. It reaches a max at 0. But now it's shifted in time for its maximum when we combine the sine and the cosine. So it's phase shifted by this amount here is phi. This is our phase shift when talking about it as a cosine curve. And if we want to talk about it as a sine curve, it's shifted backward in time this way by the amount of psi. Because it's going through 0 earlier than the sine curve, so it shifted backwards in time. So when you want to represent it as a cosine curve, you shift it forward a bit by a phase shift of phi, and if you want to represent it as a sine curve, you shift it to the left by amount of psi. And psi plus phi, this distance here is pi over 2. So this is the combined curve. It has a little larger amplitude than either the sine or the cosine, but it also has the same period. And this always happens. Whenever you have sines and cosines of the same frequency and you add them, you always end up with a sinusoidal type curve with the same frequency, just shifted in time. We do this a lot in electronics. We like to think in terms of a sinusoid or cosinusoidal curve that is phase shifted or shifted in time rather than as a sum of a sine and a cosine curve. It's easier to visualize one function shifted in time by phase shift rather than trying to figure out what this looks like, a cosine theta plus b sine theta. This tells us right away what we have. We know what the amplitude r is. It's the square root of the sum of the squares of the sine and the cosine amplitudes, and then the amount that is shifted in time is given by the arctangent of the ratio of the amplitudes. So it's much easier to visualize a combination of sines and cosines in terms of just a single sine or cosine function. This is how we use it in electronics all the time, is that when a signal goes through a network of inductors, capacitors, and resistors, a linear network like that will change the amplitude of the signal and its phase. It will shift it in phase and modify its amplitude. And that's the only two pieces of information you need to know in a linear network, is if you input a signal of a certain frequency, the phase shift and the amplitude modification of that wave will be frequency dependent, but those are the only two pieces of information you need to know, amplitude and phase shift, to determine what the output signal is going to look like, because an output signal in an electrical network is always going to be of the same frequency as the input, but just the amplitude will be modified and the phase will be shifted. It will be shifted in time. So this is a summary of what we've done so far. But this is the important equation here. We'll be using this a lot in Laplace transforms and in AC circuit analysis. I'll zoom in on that graph so you can take a look at it a little better. So that concludes this video.